observatory that isolates itself not only physically by being on Mars, as I explained, but isolates itself from its user community, then at some point things go wrong because you don't know anymore whether you're really serving it. But if you together build the best instrumentation, every time renewing it, influenced by technology and by changes in the science questions, if you have an active student fellowship program, etc., small telescopes on ASIAA, you stay well connected with the community. ESO belongs to the community. It's not a competitor. We are there to enable science for them. And by the success of the earlier program, which I inherited, of course, cannot take any credit for, I wouldn't. It's clear that after you've done this once and you build another observatory, it's a success. And you get involved in a global partnership, ALMA, and it's a success, then the member states are happy because they have invested in the organization. The staff in the organization have learned a lot of skills, and they can be applied again. And that's why they were also happy to entrust the building of the ELT to us. And there might be others in the future. And then finally, I didn't touch on this very much, ESO is what is called an intergovernmental treaty-level organization. So it's based on an actual treaty between the governments of the member states. And this treaty was ratified by the parliaments of all the countries. So it's an extremely robust structure. And that gives support at the highest government levels. And it also gives budget stability, and that allows you then again to do long-term planning. And we only start the project once we know that we have the money to complete it and operate. That means it sometimes takes a little bit longer to get going. But once you get going, as we now are for the ELT, we know we can finish it. Because the country's approved. So, last slide, what is the long-term future, the long-term strategy? We expect to continue to grow a little in membership, looking for countries with high-quality scientific communities want to join, and that have government support. And there are, of course, some of those countries. But we don't want to become somebody called the United Nations of astronomy. It's very important to have competition, so we don't want to become a world lab or the United Nations of astronomy. There is a wonderful collection of powerful telescopes on Mauna Kea, in which we were involved in many of them. The 30-meter telescope will come there, and it's extremely good to have that as a competitor, a friendly competitor, because that way science moves forward faster. The aim is to continue to operate and build world-class facilities. The ELT will hopefully not be the last project that ESO ever does. Can be in the optical, as you've seen, can be in the radio, as you've seen. It's possible that you can also get involved in observing the universe, learning about the universe from other messengers, particles or gas particles. And one example is the Cherenkov telescope array, which looks at high energy gamma rays from objects in the universe by the impact they have on the upper atmosphere, and they generate a Cherenkov light flash. If you can detect that with good angular resolution, you can work out where this came from. And that may come to ESO, but that's not decided yet. To balance multi-purpose telescopes in some experiments, and as I've shown you, we have some of our facilities all ESO, and others are in partnership. All of that's possible. So I think the future is quite bright, but it's also clear the first order of business is to keep doing fantastic science with the telescopes we have, including ALMA, and build the ELT. Thank you very much.
Thank you very much. Questions? In the 39-meter telescope, you attach smaller mirrors into a big one. It looks like with this technology, you don't have to stop at 39 meters, right? You can build it even larger.
Yes.
Is there any? Yes, but other than money, is there any limitation on technology? Then how about you can go?
So you're completely right, but in principle this can be scaled. And in fact, the original ID came in the late 90s. It started almost as a job. The engineers at ESO said, could we build a 100-meter telescope? Same principle, using. And they of course thought cannot be done. So let's first see, can we build a dome? Yes, you can actually do that. There are companies that build giant stadiums. And they went down the list and they kept going. And it was then reviewed some years later. And the conclusion was it's technically possible, but the cost would be fairly prohibitive. And you need to indeed remember, and then it was resized to where we are today, which is sort of at the limit of what we can afford and actually can do, because the bigger the mirror, the sharper the angular resolution. And that means, but also the bigger the steel structure and everything that supports the mirror, so heavier. And it still needs to track the stars as the Earth rotates under them with ever-increasing accuracy, because if you can't track accurately, then you make a very sharp mirror, but your image is blurred, as you know. If you integrate too long with your camera, then it blurs. So these things start multiplying, and that's why it is very, it's possible, but it gets very, very difficult. And the jump, you can also look at the other way around. There was a generation where 4-meter class telescopes were sort of the limit. And then with the active optics and big pieces of glass for the initial segment technology, our field went to 8 and 10-meter class telescopes, factor 2, 2.5 increase. Now the increase is more than a factor 3. And the thinking is, it's also the area, which is 10, and the volume of the build is 30. This is a pretty challenging step. Let's do that first, and then see if we can take it further.
I have two questions. First one is that how do you deal with earthquakes with EELT? And the second one is what's the role of VLTs in the era of EELT?
So there are earthquakes in Chile. In fact, the fault, the Pacific fault line runs between Paranal and Amazonas. That valley you saw, that's where it runs. And there have been serious earthquakes in that part of the world. Our telescopes have inbuilt seismic protection. The mirror is clamped very short amount of time, so that it is rigid versus the steel box it's in. It should survive. And other structures, again, the usual things. The safest place is probably the resonance. It should survive, knock on wood, because I don't want to, I hope we never see this happen. It should survive 8.5 or 9 right under it. But of course, you do what you can, and you know as well in this area of the world too, there's a lot of technology that you can use, so it's all built in. The VLT with the interferometer and the survey telescopes is an integrated system, which has a lot of attention to high angular resolution astronomy, but there are also the survey telescopes. And the ELT will be part of that same system. It will be a big dish, and it will do certain things for which it is uniquely capable. But that doesn't mean that a number of things are still not very exciting to do with the VLT. So it will simply expand the existing integrated system, and we continue to upgrade.
With the present economic exchange in Europe, do you expect you must be very good in getting the government to support you such a big effort?
So the support,
Financially.
yes. So what I try to explain is that yes, it's difficult in Europe. The interest in fundamental science is always always on the same page. But the good thing is that the countries fully support our program. They realize astronomy is as a pioneering function or an attractive function for attracting people to the sciences, that it addresses questions that are of interest to general society, and that building this kind of telescope is also quite interesting and challenging for the industries in the countries, because it's not the graduate students in the basement that build the telescope, it's serious industry that has to do it. And that combination has helped us, some hard work, that they all understood, hey, this is such a good opportunity, we support this. And I'm really grateful to the governments that they have that vision. So we should try it here as well, obviously. Yes. Yes.
So I'm feeling that data rate of all these new instruments may soon go beyond what can be handled by the individual user. Does ESO have any plan to have some facility to host those users who cannot deal with their data?
So the data rate is highest in these big imaging surveys. It's like Sloan, and the spectrographs, they usually integrate long, so the actual data rate is not that terrible. And even for Muse, which is a monster, lovely monster, but a monster, you can't do everything on your random laptop, but you also don't need a supercomputer to do it. There, my feeling is that this is a matter of a minor adjustment. To wait a couple of years, then it may be possible on normal laptops, so we've pushed a little. There are special machines, if people want to come to headquarters to do some data there, that can be done, or locally, they can often find it. So I don't think this is, for this kind of science, is a problem. For the big surveys, maybe.
Questions from students?
I was told by various authorities that the students in Taipei were extremely bright, all true, and they were also extremely forward in asking questions. I know this is a very risky statement to make, because now you will all attack me.
Please show him this is true.
Not a problem.
I'm actually curious, will ESO be part of the square kilometer array in the future?
That's a very interesting question. I don't know the answer. My view on this is extremely simple. The science case for the square kilometer array in its full glory is quite exciting. It's a world-class facility. And the ESO member states, some of them are trying to be in the SKA or join it. Others are thinking about it. And in my view, the governments of these countries have to decide, do they want to start a whole new organization and maybe reinvent a number of wheels, or do they want to be represented by ESO? And ESO would be ready to investigate this, but it's up to the government. So I can't give you a more definite answer.
Will ESO ever be interested in doing space telescopes?
Personally quite interested in this, and the mission statement, this goes up on YouTube, so the mission statement of ESO does not exclude it, but I'm keenly aware that there is a similar organization, somewhat similar organization in Europe called ESA, the European Space Agency, which is there to build launchers and all of this, but which has a very active program of science and robotic exploration, which has a lot of space science in it. So it would be quite unusual, and there would have to be a real good reason why there would be a good scientific reason to do a space mission that wouldn't be done by ESA, and it would have to come to ESO. That is sort of not very likely. There's more and more collaboration between space and ground. And some of the new space missions will need follow-up or preparation from the ground, and we talk regularly with ESA to make sure that we get on the right path there. And I think that is a more likely scenario in such a case.
Any final questions?
Yes.
What's the relation between ELT and telescope in Mauna Kea? Are they more complementary or competitive?
I think the answer is both, and I'll try to explain why. The design, there are some small differences between the TMT design and the ELT, but for example, the segment sizes are almost the same, and many of the technical problems will be the same. And the engineers talk to each other, because each one wants to be sure you learn and that you build the right telescope. By having one in the north and one in the south, you automatically get some complementarity because of the hemisphere, but you of course also get some competition, which is good. An example I often use when this topic comes up is there is pretty good competition and collaboration also at the 8-meter level. There are some instruments on the CAC that we also have and vice versa, similar instruments. And if you look at the study of the galactic center black hole, there are two groups in the world that are pushing very hard. Genzel's group in Garching, using mostly the VLT, and Andrea Guess's group in UCLA using the CAC. And without that competition, scientific competition, we wouldn't know as much about the black hole today as we otherwise had. If only one of them was doing it, there would not be as much pressure. And also, both telescopes would not have quite the instrumentation that we now have today, because it's driven by the science. And I think the same principle will apply of both competition and collaboration will apply to the big telescopes, the 30-meter and the ELT. So you should start thinking about writing proposals. Good.
More questions? Oh, students.
So just curious, so what is the best, or say, the top 3 discovery in your mind that was made or were made available by the ESO facilities?
We have a list of these on our website, the top 10 discoveries. So you go to www.eno.org, but it certainly includes the first image of an exoplanet. There were discoveries early on in the early 2000s about gamma ray burst objects at redshifts, really high redshift, and the galactic center black hole. Much work was done following the work on the NTT. Was done with the VLT by Genzel. That really changed the field. You understand the outreach department makes list of these so that if the DG forgets, then you can look it up.
I have a stupid question. What is the white line in your picture?
What is the?
The white knight.
White knight.
Here? This?
No. Right hand side.
This? That's the Milky Way. No?
The red white knight.
The line, the red line, maybe.
Ah. Yes. That? No, that's a laser. That is a laser. So first of all, I think you've all understood this is, you see here, the top of our headquarters, part of Paranal, the ELT, part of ALMA, LaCia. This is a collage of our observatory. So our outreach department calls this the ESO universe. They're not all in that location, just to be clear. This is a laser beam sticking out, pointing out of our UP4, which hits the sodium layer at 90 kilometers up in the atmosphere, provides a spot, which we know is a spot, and we image that instantaneously back at the telescope. With a deformable mirror, we then make sure that the light really is focused in a single point. And if we manage to do that, we correct for the laser beam for the turbulence in the atmosphere. And then not only near that, exactly at that spot, but in a small area around it, you have also corrected for the turbulence of the atmosphere. So it's an artificial guide star that allows you then to make sharper pictures of the night sky. It looks great, huh? It's lasers sticking out, but that's what it is.
Okay, I think it's a good place to stop. But to conclude, I want to know that ESO is not just an observatory, but they also provide studentship. So if you are interested in working with this great instrument, I encourage you to come talk to Professor Zeeuw. So let's thank him for a great talk.